Okay, here's an example of expected value for the Powerball lottery. And it makes a lot of sense, actually. You can use it for a lot of things, but we don't have Powerball in Hawaii, obviously, but it's a big thing on the mainland. For students of rhetoric is basically logic applied to persuasive purposes. We will cover this a little bit later in the course, just briefly. You might think, what's in a name? Uh, Powerball. Why not call it something else? Well, it sounds powerful, doesn't it? Is it really? Well, let's examine. Let's suppose the ticket costs $3. You stop by 7-Eleven and you're trying to decide. You can spend $10 on a solid lunch. That's kind of expensive, but this is Hawaii. Or you buy 2 lottery tickets, let's suppose they sell them in Hawaii, and have their mystery and meat drink combo. Delicious. So you want to figure out, what's it worth? What's the expected value of buying a ticket? Okay, let's suppose there's only 2 consequences, winning and not winning. So the utilities of winning, 20 million. It's usually big. It can be bigger than that, right? Just to make it simple for the sake of this example, let's say just 20 million. Utility of not winning, well, you just lose your $6 because you just bought 2 tickets, right? However, these aren't enough. You just can't balance these out. You also need the probabilities associated with winning and not winning, which many lottery ticket buyers often are not aware of. They just say it's low. Can you give a number to that? Small. Well, like how small? Really small. That's not very precise. So let's suppose, in this case, in fact, when you look it up, for multiple state lotteries, the rough, it varies, but it is small. So 1 out of 120 million, minuscule. The probability of not winning, 1 minus 1 out of 120 million, meaning basically your chances of not winning are pretty darn close to 1. Okay. By the way, if you're curious how they get that number for winning, this goes back to one of our earlier lectures on combinatorics. So I have this out here for those who read it. If it makes sense, great. If not, don't worry about it. So when you calculate it in terms of your expected value, probability of winning times utility plus probability of not winning times utility not winning, stick in those numbers. For $6 you spend, you stand to lose on average $5.84 on average. Moral, just do something else with that $6. Powerball is a little bit more complicated, a bit more enticing. They up the odds, okay? So for Powerball, you get 5 white balls ranging from 1 to 59, 1 red is drawn, ranging from 1 to 39. The order doesn't matter, probabilities are a little better, and there's more prizes. It's not just win or not win, right? So here we go, a very brief, from the website and whatnot, a very brief outline of Powerball winning. So here's how it kind of works. If you get these and the match, you get the grand prize. Chances of winning, 1 in how many does? 1, 2, that's 2 places, that's millions. 1 in about 200 million, not 20, 200 million. $200,000, not bad. 1 in 5 million. Oh, not so good. And on and on and on. Okay? So these are various outcomes. These are like your consequences for expected value. These are your probabilities. Yeah? Here are your utilities. Okay, so there we go. We can map it straight to expected value. So the expected value, I'm not going to go through all this. I'm just going to outline the idea of expected value. Expected value, and I estimate here, I don't do it exact because we don't need the exact. This isn't a math course. It's a concepts course. Come on. So expected value of buying a ticket, that's your action. Well, again, expected value equals the probability of each of the consequences times the utility of each of those consequences. So the probability of hitting the jackpot times the utility of hitting the jackpot. Small probability, but big payoff, right? Times, and then plus, sorry, not times, plus the next thing. The next consequence is you win the 200,000. That's a small probability also, but not as small as the first one. Times the utility, which is 200,000, pretty big, pretty good, and so on and so forth. This adds up all the various things. When you do the overall calculation, very roughly, it equals still minus 75 cents. So that means for on the dollar, if you buy a $1 ticket, you will lose on average 75 cents. It's a losing bet. Did you think otherwise? It's like when you go to Vegas, do you expect to win on average? No, what did they say? The house wins on average. Why is that? Well, we just say so because it's Vegas, but the why behind that is what this course seeks to explore, as well as far, far more, undergirding a whole lot of our institutions in the world today. It's not just Bayes, as I mentioned before, running the internet, running your phones, running learning networks and data collection and all that. There's a whole series of other things: insurance companies, Vegas, betting, the Fed. The Federal Reserve is one of the most powerful institutions in the United States. It's often thought to be maybe more powerful than the presidency. And they've got a lot of things that they go on there. They're running calculations using economic models, and they're using in various inductive type schemes to basically run the economy. Okay, so the point here is that on average, for the dollar, you lose 75 cents. It's not in your favor. Horrible advertisement. Doesn't it look good? Aren't you enticed? Don't you want to buy now? But wait a second. If I lose 75 cents on a dollar, that's pretty crappy, right? If you got $100, you're a student, poor student, you don't have much money. Suppose somebody gives you, mom and dad, auntie, $100 for a gift, and someone says, "Hey man, I got this bet for you. For every 100 you put in, you're gonna lose 75. You want it? You want to take my bet?" The answer is no. But if you got advertisement like this, you might go, "Yes, Powerball. Ooh." All right, that's the end of this sarcastic lecture.